Hi, today we're going to explore topic 310, part one. This topic is actually trigonometric equations and inequalities. Today we're going to focus on the equation side of things, and we're going to look at what it would look like to solve a trig equation, what kind of supporting work that you would need, all of those kind of things to make things go smoothly. So let's start by this first question, example one. We have sine of x equals 1/2, and then equation two, sine to the negative 1 of 1/2 equals x. So the first question here is, are they equivalent? Well, here's a circle, and we know that at this particular point, we have pi over 6. And at this particular point, standard position around to here, that would be 5 pi over 6. So if we think about what these statements mean, this first one, sine of x equals 1/2, means that any value, and let's say one time around the circle, that any value that would make this statement true would be a possible solution. So we would have this angle that we just looked at here, which is pi over 6. And remember, that's going from the positive x-axis up to there. And we would have the equation in quadrant 2, which is 5 pi over 6, which would be the equation going from here, or the the angle, excuse me, going to there. So we have two solutions that fall between 0 less than or equal to x less than or equal to 2 pi. But if we look at this equation, remember this means what angle has a sine value of 1/2 within the restriction. So over here, it's what angle has a sine value of 1/2 within the restriction. So if I remember from the last lesson, when we are looking at sine is restricted from negative pi over 2 to pi over 2. So we would have to find a solution within that restriction mark. And that means that only the pi over 6 answer would be possible. So within the restriction, there is one solution. So then the answer to this question should be no, because each equation is producing a different quantity of solutions. So as you look at the explanation down here, if we're looking at the unit circle, we have these angles down here. We call them theta. Just make sure within a problem you're working at that you're consistent. If your restriction is in theta, then probably your answer should be in theta. If we're looking at this up here, our angles were in terms of x, so we have our answers in terms of x. And based on the restriction, when we solve these two equations, we can see that we had different possibilities. So here we had two possibilities. Here we only had one. So as a result, when we're solving equations involving trigonometric functions, we often have to modify our solutions or take into account any domain restrictions that they might have as we're working through a problem. So we're still going to be needing our restriction marks where they apply. Okay, so let's go down to just general solving. So when we're looking at general solutions, that means we're looking at a situation where we have infinitely many solutions. We can't list them out because we have no ending to where they might occur. Remember, your circle does not stop. There is no beginning or end of a circle. So we just have to keep using and finding our solutions. And that is impossible to list out. So the way we go about that is when we write a general solution, we're going to write an equation that will represent all possibilities. So for instance, let's look at the first one here in our box. We have sine of x equals 1/2. So we know that we can have an angle that happens to fall in the first quadrant that is going to be equivalent of 1/2, or it's going to be pi over 6. That's the angle. that if we keep going forever and ever and ever around the circle, any angle that terminates at this same side, remember we call those coterminal angles, so any coterminal angle is going to have that same solution. So we write an equation that would represent all solutions that would start and stop here at pi over 6. So we do that by writing that angle down, pi over 6. And then if I'm at pi over 6, to get back to pi over 6, I have to travel around the circle one time, which is a distance of 2 pi. So then we add 2 pi, and we're back to our variable of k that we talked about last time. K is the letter that represents an integer. And so sometimes we say that k included in the set of integers, and we have that Kes situation going on. But because there are two possibilities when this can occur, we can also have another angle in that same one rotation around the circle that has the same sign value of 1/2, and that happens to be over here at 5 pi over 6. So what that means then is if I'm at 5 pi over 6, I've got to travel all the way around the circle to stop again, and to stop again, and to stop again. And all of those angles, remember, are called coterminal angles. So now we're going to write down the second angle that would work for this situation. We're going to add 2 pi to it to show that we're traveling around the circle one time and stopping at the same place. And the k, remember, is the integer. So that's the rotation. So we don't like go halfway around the circle and stop because that wouldn't be the same value. All right, so let's look at the next one. Cosine of 1/2. So we know that we have a cosine value of 1/2 in the first quadrant, and that's going to be pi over 3. And then we also have an angle that has a cosine value of 1/2 in the fourth quadrant, and that's 5 pi over 3. So because those are at different locations, we're going to write one equation for each angle. So we would start with the pi over 3, we add 2 pi to it, and we use our k to represent whole number rotations of integers. And then the second angle was 5 pi over 3, so we write that, plus 2 pi, and once again the k represents all integers in that rotation. So it looks like that. So that's how we would do an example of sine and cosine. We're going to do an example of tangent. So this is saying, where would I find a tangent value of 1? And we know that's going to have to happen in a multiple of pi over 4, because the only way we can get a 1 is if the cosine and sine values are the same. So we know we have this in the first quadrant, but we also know in the third quadrant, we have another situation because a negative divided by a negative would also be a positive. So we could also be talking about 5 pi over 4. In this situation, can you see how both of these make one big long line? So there's part of the line in the first quadrant, the other half of the line is down here in the fourth quadrant. That makes this situation different from these. You can see each of these had their own location of their angle. They were in a different place. This one, they all line up on the same line. So technically, I only need to write one equation to represent all angles of pi over 4 multiples, because if I bounce back and forth, let's say I start at pi over 4, but I only go halfway around my circle, I'm at the other possible solution. And if I go halfway again, I'm at the other possible solution. And one more halfway, I'm back down here at this possible solution. Another halfway, I'm back up here. So instead of rotating 2 pi like we did for sine and cosine, we start with that smallest angle, which is pi over 4, but we're only going to rotate halfway around the circle. We're still going to do it in integer rotations so that we stop at either this point or this point, but we only need one equation to capture all solutions. So in this, we can see that we're only going to need that one solution. So sometimes that may work out where you're going to need one solution, one equation to represent all solutions, and at other times you're going to have to write multiple equations to represent all solutions. Okay, so let's practice. So the first thing that is important when you're reading the directions is you have to ascertain whether you're going to have an equation that represents all possible solutions, or if you're going to have a list of answers because your domain has been restricted. So in this case, right off the top, you can see find all solutions. So what that means for you in terms of this problem is you're going to write equations. And the equation is going to represent the solution. So then the next thing we're looking at is what equation or what values are we talking about? And we are talking about the cosine of x equaling negative root 2 over 2. So the first thing in my work is going to be a quick sketch of where these angles might be. So where would I find angles that have a cosine value of negative root 2 over 2? I'm going to find one in quadrant 2, which is going to be 3 pi over 4. And then I'm going to find one in quadrant 3, which is going to be 5 pi over 4. So do they line up on the same line? No, because one of them's here and one of them's here. This one would have to be on the bottom half of the line here for that to be true. So in this case, we need two equations. Not that I expect you to write that when you're doing your problems, but it is notes. So I do want you to write in there that you're going to need two equations. So to write our two equations, we're going to take x equals, because our symbol we use there is x. If the symbol there is theta, then you would say theta. If it's beta, then you would say beta. All right, so I'm going to take x equals, I'm going to do my first angle, 3 pi over 4. And then I want to go all the way from here around the circle and stop back at the same place. So I'm going to rotate around the circle 2 pi. And then we add our k to represent whole numbers. And we say k included in the set of integers. Okay, so then we go to our second angle, which is down here. We're going to say x equals 5 pi over 4. Plus, and then we're going to rotate from 5 pi over 4 all the way around the circle back to the same position where 5 pi over 4 is. So I'm going to add 2 pi. I'm going to have my k in here for whole number rotations. And then I'm going to say k included in the set of integers. And that's going to represent the solutions, all possible solutions for this situation. Okay, so let's look at the next one. So in example 2, you can see it says find all solutions. The equation that we're talking about is right here, where sine of x equals negative 1. So we're going to draw our picture, rough sketch quickly. Where would sine be negative 1? It's going to be right down here on this axis, which is 3 pi over 2. So then I'm going to write my equation by saying x equals, so x is the variable we're using right here. The smallest angle, or in this case, the only angle, is 3 pi over 2. We're going to go all the way around from 3 pi over 2 until we land back at 3 pi over 2. So we're going to add 2 pi, k, and then we're going to have k included in the set of integers. All right, let's look at the next one. So find all solutions. So equations are what we need in terms of what our solution or answers are going to look like. Here is our equation right here. That does not look like a unit circle value, but hopefully by now you do realize that that's the same thing as tangent of x equals root 3 over 3. We worked on tangent values last class. So we have two places where this can be true, where tangent is root 3 over 3, and that is in this quadrant, which is pi over 6, and it's in this quadrant, which is 7 pi over 6. Now, can you see how both of these line up on the same line here? Then we don't have to write two equations. In fact, I would expect that you not write two equations. So you're going to say x equals, you're going to pick the smallest of the two, which starting from the positive x-axis and rotating counterclockwise would put us at pi over 6. But instead of adding 2 pi to get back around to pi over 6, I'm only going to add pi to get over here to 7 pi over 6. So I'm going to add pi, and my k, remember, is k included in the set of integers. All right, so that's the three examples that we have right now. And so this is basic finding all possible solutions, general form. And so if you want to write yourself a note in here, this means finding all solutions. Right here. Okay, so when it says all solutions, you're looking for equation. So now we're going to shift gear for a couple of problems where we're not finding all solutions, we're finding specific values to represent our answers. Okay, so in this next section, these problems that we're going to be looking at now are finding solutions. So everything now is just kind of actually solving equations. So let's review a few things here. Trigonometric equations, we're going to isolate the trig function to one side of the equation to get it by itself. And then we're going to find the angle measure on the unit circle that satisfies the equation. We are going to consider any domain restrictions. So we have to remember that sometimes when we're solving, we may have to put those restriction marks on our graphs still. And then we're going to list the solutions or the general solution, which would be the equation. Okay, so the difference in what we looked at a minute ago and now is we have to decide, is it going to be a list or is it going to be an equation to represent the solutions? Okay, so look at example 4. So when you read this, you can see that it says all values of theta gives an equation. So that means we're looking for an equation in terms of our answer. It does not restrict it or give us any kind of restriction like example 5 does, where it says solutions from 0 to 2 pi. So the first thing we need to do in example 4 is to isolate the sine theta to one side. So I'm going to divide both sides by 6 to get sine theta by itself. So now I have 3 root 2 over 6, and 3 over 6 simplifies to 1/2. So I have sine theta equals root 2 over 2. So now I need to think, where would sine be positive? Sine is positive in the first quadrant, and the angle in the first quadrant that has root 2 over 2 is pi over 4. And then I have an angle in the second quadrant that also has a sine value of root 2 over 2, and that is 3 pi over 4. So now I want to look and see, are those angles lined up on the same line? In other words, do they make a line when I look at my graph? And they do not. That means my answer will need to be two separate equations. So the variable that we're using is theta. So we're going to say theta equals the smallest angle, which is pi over 4, plus we're going to rotate from pi over 4 all the way around the circle till I get back to pi over 4. So I'm going to add 2 pi k, and that k included in the set of integers. And then the second solution is going to come from this angle over here, which is 3 pi over 4 plus 2 pi k for integer rotations, and then that's going to be k included in the set of integers. And so that's how you would solve an equation in the tangent functions or in any of the functions that look something like that. So isolate that variable and go from there. Okay, example 5. Let f of x equal 3 plus 2 cosine x and g of x equals 2 in that xy plane. It says what are the x coordinates? So the x coordinates means that we're looking at x equals type solutions of the point of intersection. So what does the point of intersection mean? That means f of x has to equal g of x on the graph of f and g for this restriction. And you might check your note page. I noticed that there were some discrepancies, like in the question, it was saying in terms of x, and in the restrictions, it was saying theta. Just make sure they're the same. You can change them to be either way. I think I changed this one from theta in the restriction to an x. Okay, so this is telling me in my reads, my first and second read, this is what I need to do. I need to set these equations equal to each other. So I'm going to have 3 plus 2 cosine x equals 2. And the goal, remember, is to get the trig function by itself. And we can see that we have restricted domain here. Okay, so once I set these equal to each other, I'm going to get cosine by itself. So I'm going to subtract 3 to both sides, and now I have 2 cosine x equals -1. Then I'm going to divide both sides by 2, so I have cosine x equals -1/2. All right, so now I have my equation. So now I am looking at where on this graph would cosine have, at what angle would have a cosine value of -1/2. So from our work with unit circles, we know we have one up here, which is 2 pi over 3. And we know we have one down here, which is 4 pi over 3. So if they're not on the same line, then we need how many equations? 2. Okay. Now go back to this piece right here. It says restricting it from 0 to 2 pi. So that's not saying all. So if it said all, we would write two equations. Because it gives me a restriction, I simply need to list the values or the angles that would work. And the angles that would work would be 2 pi over 3, and then also 4 pi over 3. So you can see that these two type of answers look very different. This is a couple of equations that represent every single angle possible, whereas this is a list of angles because we have a restriction, and from 0 to 2 pi simply means we only have to find the answers one rotation around the circle. All right, so one more little tidbit about notation. We'll work a couple more problems, and then you'll be able to go work on your daily practice. So when we have trig functions and we're raising them to exponents, we have to be careful about our notation. And we don't want it to be overly complicated or ambiguous when we're looking at it. We want to see exactly what we're talking about. So what I'm referring to right now is this situation where we have a power of 2 that only is part of the x within the sine function. So we're only squaring the variable of x here, not sine x. In other words, it's not sine x times sine x. It's sine with two x's being multiplied inside. And it's not the entire expression. So we want to be very, very mindful of where we put those powers because that can change things. So what we're going to do is when we write something like this, or we're meaning something like this, we're going to use that power between the sine and the x. So for instance, if I had sine x to the power of 2, then that is sine squared x. And so we need to be mindful of this notation and not let it become confused with something like this. So keep your notation straight. All right, so go ahead and isolate. So we're going to pause your video. I want you to isolate sine to itself. We get sine by itself, excuse me, isolate it. And then we'll proceed with the solution from there. Pause your video. Okay, so we've isolated our trig function on the left-hand side. Remember, when you take the square root, you need that plus or minus, or you're going to lose part of your solutions. So I have plus or minus square root of 3 over 2 because the square root of 4 is 2. So then I'm looking at my equations. So plus and minus means that I have 2 positive and 2 negative. So the two places that sign is positive, root 3 over 2, would be in the first quadrant and the second quadrant. So that's going to be pi over 3 and 2 pi over 3. Then the second place, or the second set of solutions, would be when square root of 3 over 2 is negative, and we're going to find those in the third, which would be 4 pi over 3, and the fourth, which would be 5 pi over 3. So we have 2 positive and 2 negative for a total of 4 solutions. So if you forgot your plus or minus, then you would probably be losing your negative solution. So you would have just lost 2 of your answers. So it's very, very important to keep that in mind. Since we have a restricted area that we're looking for solutions, then our answers are going to look like a list. Okay, so that means our variable that we're using in our problem is theta. And that should probably say g of theta here as well. So we can make that note. So everything should all be lined up. So then in this particular problem, I would have theta equals pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Let's see, I can't hardly read that one. Okay, and so that's what it would look like if you have a problem that you're going to solve with a restriction. It'll be a list of answers. If you're going to have a problem that you solve that's all solutions, then you're going to have equations that will represent your answers. Okay, so go ahead and do your first and second read on 7, and then see if you can, what you can do with those functions, because as you notice, there's 2 cosines. So if we look at this, we can see that all solutions, but then it restricts it right here from 0 to 2 pi, and it gives us this equation. So the problem with this one is I can't move one trig function to one side or the other and not have it isolated because I have more than one trig function. So in a situation like this, we're going to move everything to the same side. Excuse me. So we're going to have cosine squared theta plus cosine theta equals 0. And then in order to solve, we need factors. And in order to factor, we need to actually factor. So we're going to pull out the GCF here, which is going to be cosine of theta, leaving us with cosine of theta plus 1 from each of the terms that we took it out from, equal to 0. And so then what we do is we set each factor equal to 0 and solve, just like any other algebraic situation where we have factored and then solved, but now we just have to deal with tangents, or not tangents, with trig functions, excuse me. All right, so the first one is this factor right here. So I'm going to say cosine of theta equals 0, and I'm going to draw my graph for this factor. And the only places where cosine can equal 0 is at pi over 2 and 3 pi over 2. So I expect a graph. I expect both points labeled clearly on the graph, legibly, and with the factor itself. Okay? So then the next one would be the second factor, which is the cosine theta plus 1. So we're going to do cosine theta plus 1 equals 0. So cosine of theta equals -1. Then we're going to draw a graph for this factor. And there's only one place that cosine can be -1, and that's right here at pi. So then we need to be mindful of how we leave our answers. We're given a restriction. And so when we have a restriction, our answer is a list. So the variable that we're using in this problem is theta. So we're going to have theta equals pi over 2 and 3 pi over 2 from the first factor and pi from the second factor. All right, so let's go to our last example, example 8. And so it looks like all the variables are now in terms of x, and it says that we have f of x equals 2 sine squared x. We have g of x equals √3 sine x. In an xy plane, what are the x coordinate, or what is the x coordinate for each factor? But in this case, when we see that, we're thinking of x equals. And the point of intersection, well, what are we asked to intersect? We're asked to find when f of x equals g of x. That's the intersection. And we have 0 to 2 pi, so we have a restriction. All right, so first question to ask yourself is it going to be a list of answers or is it going to be equations? And when you see the restriction, you know it's going to be a list of answers. It tells us to find the point of intersection, so that's when f of x equals gx. So that means we're doing 2 sine squared x equals square root of 3 sine x. So we're going to have multiple trig functions here. So we're going to get them all to the same side and see what factoring techniques we can use to break them into factors. Set each factor equal to 0. Do a graph of each factor once you've set it equal to 0 to get your solution. So go ahead and pause your video one last time and see what you can do to get to your answers here, which will be a list of x equals. All right, let's see how you did. So we isolated, we got them to the same side. We factored out as sine x because that's what was common to both pieces. So we have these two factors. So we set the first factor to 0, and the only place on the circle that sine can be 0 is at 0 or 2 pi. Notice in our restriction, it does not say equal to 2 pi. So your answer must be 0. If you give an answer of 2 pi, you've exceeded your restriction, so it would not be counted for anything partial or anything else. Because that means you're not being mindful of your restriction. The second factor, 2x minus √3, set equal to 0, so I moved the 3 over, divided by 2, so I got sine of x is √3 over 2, which happens on the unit circle at pi over 3 and 2 pi over 3. So my list of final solutions then from the first factor, x equals 0 and pi, and from the second factor, I get pi over 3 and 2 pi over 3 for a total of 4 solutions. Okay, so that concludes part 1 of our notes. Next section, we're going to look at more about inequalities and go in a little bit more practice with equations. So be sure you do your daily practice so you're ready to take the skills that we learned today and we can add on next time. Thanks so much, guys. Bye.